Fewer than a dozen distant Kuiper Belt objects out of thousands catalogs show orbital clustering. Unusual enough to suggest the gravitational influence of an unseen body far beyond Neptune. This is the life story of the idea of a hidden ninth planet, not as conspiracy, but as a scientific hypothesis shaped by observation, uncertainty, refinement, and the long patience of astronomy. A lesser-known fact is that early orbital simulations indicated that a planet, roughly 5 to 10 times the mass of Earth, could produce the observed clustering, a test result dependent on limited data sets and evolving models. Its birth begins with a problem of motion. Objects in the outer solar system do not move randomly. Their paths follow gravitational rules. When several of these objects appeared to share similar orbital alignments, it raised a question. Why would independent bodies behave as if guided by a common influence? A lesser-known fact is that orbital alignment of distant objects deviates from random distribution at statistically notable levels. Though estimates vary depending on sample size and selection bias, reflecting a design compromise in observational completeness. The parents of the hypothesis were not secrecy or suppression, but calculation and anomaly. Researchers like Konstantin Batygin and Michael Lee Brown proposed in 2016 that a distant, massive planetophon called Planet Ninecut explained these patterns. The idea emerged from modeling, not direct observation. A lesser-known fact is that initial simulations required tens of thousands of iterations to test stability of orbital configurations. A production issue tied to computational limits. Early decisions in framing the hypothesis were cautious. The planet was not claimed as discovered, but inferred. Its properties, mass, orbit, distance were estimates, constrained by available data. A lesser-known fact is that predicted orbital periods for such a planet range from 10,000 to 20,000. From 10,000 to 20,000 years, a supply constraint of time that makes direct observation difficult. Childhood of the idea was marked by skepticism and testing. Other astronomers questioned whether the clustering was real or an artifact of observational bias. Surveys of the outer solar system are incomplete, and detection depends on where telescopes are pointed. A lesser-known fact is that sky surveys cover uneven regions, with some areas observed far more frequently, introducing sampling bias into object detection. Training realities of astronomy shaped this phase. Observers relied on faint signals, long exposures, and repeated measurements. Detecting a distant planet required distinguishing it from background stars, noise, and transient objects. A lesser-known fact is that detection of faint objects often requires stacking multiple images over hours or days. A crew training detail in observational astronomy. Small changes mattered more than large claims. Refinements in data analysis, corrections for bias, and inclusion of new objects gradually improved the reliability of patterns. A lesser-known fact is that adding even a few new Kuiper Belt objects to datasets can significantly alter statistical significance, a test result reflecting sensitivity to sample size. Misunderstandings emerged outside scientific circles. The hypothesis was sometimes framed as a hidden object deliberately concealed, rather than a predicted body not yet observed. This shift in narrative changed perception of the idea. A lesser-known fact is that public interpretation of scientific hypotheses can diverge significantly from original intent, a psychological effect tied to framing and language. Growth of the hypothesis came through accumulation of evidence and refinement of models. Additional objects were discovered with similar orbital characteristics, strengthening the case for a common influence. A lesser-known fact is that some newly discovered trans-Neptunian objects exhibit perihelion clustering consistent with Planet 9 models, though alternative explanations remain under study. Standardization followed. Models of the proposed planet converged around certain parameters: mass, between 5 and 10 Earth masses, an elongated orbit, in a distance of hundreds of astronomical units. A lesser-known fact is that 1 astronomical unit equals approximately 150 million kilometers, highlighting the immense scale of the proposed orbit. The system around the hypothesis matured. Telescopes were directed toward predicted regions. Surveys were designed to maximize detection probability. The search became systematic. A lesser-known fact is that detection of a distant planet depends heavily on its current position in orbit, which may place it in regions of the sky with high background noise, a weather and terrain impact in observational terms. At its peak, the idea gained widespread attention, not because it was confirmed, but because it represented the possibility of discovery in another major body in the solar system, found through indirect means. A lesser-known fact is that previous discoveries of planets like Neptune were also predicted mathematically before observation, marking a historical precedent. A defining scenario unfolds in simulation rather than battlefield. Models run, parameters adjust, and outcomes are compared with observed data. When alignment improves, confidence grows. When it does not, models change. A lesser-known fact is that orbital simulations must account for gravitational interactions over millions of years to test stability, a computational challenge in celestial mechanics. Why it works in those moments is because gravity leaves traces. Even unseen, a massive object influences others. Patterns in motion become clues to presence. A lesser-known fact is that gravitational perturbations have been used historically to infer unseen masses, including dark matter in galaxies. The cost is patience. Years of observation may yield no direct detection. Instruments reach limits. Time becomes a constraint as much as technology. A lesser-known fact is that telescope time is highly competitive, with proposals often exceeding available observation slots by factors of 3 or more, a supply constraint in research. There is also uncertainty. Not all data supports the hypothesis equally. Alternative explanations such as collective gravitational effects of many smaller objects remain possible. A lesser-known fact is that some models suggest a distributed mass of smaller bodies could mimic the influence of a single large planet, a countermeasure hypothesis in scientific debate. Fatigue appears in subtle ways. Researchers must balance pursuit of one hypothesis with broader scientific goals. Focus cannot be absolute. A lesser-known fact is that long-term research projects often require periodic reassessment to justify continued resource allocation. A command doctrine shift in scientific planning. Old age, if it comes, will not be dramatic. The hypothesis will either be confirmed through observation or gradually replaced by better explanations. There is no single moment of collapse. A lesser-known fact is that many scientific hypotheses are refined or abandoned without clear endpoints, reflecting the iterative nature of research. New technologies may shift the outcome. More sensitive telescopes, wider surveys, and improved computational models increase the chance of detection or refutation. A lesser-known fact is that next-generation observatories are expected to detect fainter objects than current systems by significant margins, expanding search capability. Its legacy is already forming. The hypothesis has driven new surveys, improved models, and deeper understanding of the outer solar system. Even without confirmation, it has shaped research direction. A lesser-known fact is that hypotheses can stimulate data collection and technological advancement regardless of eventual validation. What later systems learn is the value of inference. Not all discoveries begin with observation. Some begin with patterns that demand explanation. A lesser-known fact is that indirect detection remains a core method in astronomy, from exoplanets to black holes. And so it continues, not as a hidden truth withheld, but as a question still open. The outer solar system remains vast, partially mapped, and full of possibility. A lesser-known fact is that the Kuiper Belt extends far beyond Pluto, containing thousands of objects with orbits still being cataloged. The idea of a ninth planet does not rely on secrecy. It relies on evidence, tested and retested, refined over time, whether it becomes a confirmed world or a stepping stone to better understanding. Its life is defined by process rather than revelation. Roughly 90% of objects larger than 100 kilometers in the inner Kuiper Belt are believed to have been detected, yet far beyond that region the completeness of surveys drops sharply, leaving vast volumes effectively unsearched. The hypothesis enters its next phase in that gap where prediction is precise enough to guide effort, but observation is still constrained by distance, brightness, and time. A lesser-known fact is that telescope sensitivity decreases rapidly with distance, requiring exponentially longer exposure times to detect objects only marginally farther away. A design compromise of observational physics, focus narrows to search strategy. It is no longer enough to know that a planet might exist. The question becomes where and how to look. Predicted regions of the sky are mapped based on orbital models, but those regions are large thousands of square degrees. A lesser-known fact is that scanning just 1 square degree of sky at sufficient depth can take hours of observation. A supply constraint that limits coverage speed. Instrumentation shapes the effort. Wide-field telescopes trade resolution for coverage, while narrow-field instruments offer detail but scan slowly. The search becomes a balance between breadth and depth. A lesser-known fact is that wide-field surveys can cover areas hundreds of times larger per night than high-resolution telescopes, but with reduced sensitivity to faint objects, reflecting a production issue in survey design. Data handling becomes central. Each night of observation produces massive data sets requiring processing, filtering, and verification. Automated systems flag potential candidates, but human review remains essential. A lesser-known fact is that false detections caused by noise, cosmic rays, or moving artifact scan outnumber real objects by significant margins, requiring layered validation as a countermeasure. Training of observers adapts. Skills shift from direct observation to interpretation of processed data. Recognizing patterns in noise, distinguishing motion across frames, and validating orbital consistency become core tasks. A lesser-known fact is that identification of distant moving objects often relies on detecting shifts of just a few arcsecants across multiple images, a crew training detail requiring precision and patience. Small refinements continue to matter. Improved calibration of instruments reduces systematic errors. Better algorithms increase detection efficiency. Even slight gains in sensitivity expand the searchable volume significantly. A lesser-known fact is that a 10% improvement in detection sensitivity can increase observable volume by more than 30%. Due to the cubic relationship between distance and volume, a test result and survey capability, alternative explanations remain active. Some researchers propose that observed clustering may result from observational bias or collective effects of many smaller bodies rather than a single planet. The hypothesis competes within a framework of multiple plausible models. Fact is that statistical significance of orbital clustering varies depending on inclusion criteria for objects, highlighting uncertainty in dataset selection. A defining scenario in this stage unfolds over years. A region of sky is scanned repeatedly. Data accumulates, candidates appear and disappear under scrutiny. Most are eliminated. The process is slow, iterative, and often inconclusive. A lesser-known fact is that confirmation of a new, distant object requires follow-up observations over months or years to establish a reliable orbit, reflecting a weather and terrain impact in terms of observational windows. Why the hypothesis persists is tied to consistency of patterns. Even as data sets grow, Certain alignments remain difficult to explain without an external influence. The models do not prove existence, but they maintain plausibility. A lesser-known fact is that gravitational modeling can reproduce observed orbital distributions more accurately when including a distant, massive body. Though alternative fits remain possible, the cost becomes temporal. Careers may pass without definitive answers. Research cycles extend across decades. Patience is not optional, it is structural. A lesser-known fact is that long-term astronomical surveys often span 10 to 20 years, reflecting the slow dynamics of distant objects. There is also competition for resources. Telescope time, funding, and attention must be shared across many projects. The search for a single object competes with broader scientific priorities. A lesser-known fact is that allocation of observation time is often determined through peer-reviewed proposals, with acceptance rates sometimes below 30%, a command doctrine, shift toward merit-based distribution. Fatigue appears as recalibration. Researchers refine expectations, adjust models, and accept uncertainty as part of the process. The goal shifts from immediate discovery to incremental understanding. A lesser-known fact is that iterative modeling improves predictive accuracy over time, even without direct confirmation, demonstrating value in refinement. Meanwhile, technology advances. New surveys expand coverage. Future observatories promise deeper scans and faster data processing. Each advancement reduces the unknown fraction of the outer solar system. A lesser-known fact is that next-generation survey telescopes are expected to image the entire visible sky every few nights, dramatically increasing detection opportunities. The hypothesis adapts with each new dataset. Parameters, shift mass estimates, orbital paths, probable locations. It is not static. It evolves alongside evidence. A lesser-known fact is that updated models have narrowed potential search regions compared to initial estimates, improving efficiency of targeted observation. Over time, public perception stabilizes. The idea of a ninth planet becomes familiar, less sensational. It is understood as a possibility, not a certainty. A lesser-known fact is that repeated exposure to scientific hypotheses can normalize uncertainty, reducing initial overreaction to speculative claims. Replacement, if it comes, will likely be quiet. Either a detection confirms the hypothesis, or accumulated data supports alternative explanations more strongly. The transition will be gradual, not abrupt. A lesser-known fact is that many scientific ideas transition into consensus or rejection through accumulation of evidence rather than single events. Its legacy continues to build. The search drives improvements in instrumentation, data analysis, and understanding of distant solar system dynamics. Even without confirmation, it expands knowledge. A lesser-known fact is that research driven by specific hypotheses often yields broader discoveries, including new classes of objects. What remains at the edge is not secrecy, but distance. The outer solar system is vast, dim, and slow to reveal its contents. Exploration proceeds not by revelation, but by persistence. A lesser-known fact is that light from objects hundreds of astronomical units away can take many hours to reach Earth, emphasizing observational delay, and so the story continues in that distant region where prediction meets patience. The possibility of a ninth planet remains open, shaped not by hidden agendas, but by the limits and progress of observation. Nearly 5 billion kilometers from the Sun marks the orbit of Neptune. Yet the hypothesized orbit of a ninth planet could extend 10 to 20 times farther, into regions where sunlight is 400 times weaker than at Earth. The search enters its most demanding phase here, where detection is no longer limited by theory, but by the extreme faintness and slow motion of anything that might exist. A lesser-known fact is that reflected sunlight from objects at such distances can be millions of times dimmer than the faintest stars visible to the naked eye. A design compromise of inverse square light laws, motion becomes the key indicator. A distant planet would not appear as a bright moving object, but as a barely shifting against a dense background of stars. Detecting that motion requires images taken days, weeks, or even months apart. A lesser-known fact is that apparent motion of distant solar system. Objects can be less than 1 arcsecond per hour, a test result that pushes limits of detection accuracy. Search strategies adapt again. Instead of scanning blindly, astronomers revisit the same regions repeatedly, comparing images over time to detect subtle shifts. This method reduces false positives, but increases time investment. A lesser-known fact is that repeated imaging campaigns can reduce false detections by over 50%. Acting as a countermeasure against transient noise and artifacts, instrumentation faces physical limits. Atmospheric distortion affects ground-based telescopes, while space-based observatories are limited by size and availability. Each system has strengths and weaknesses that shape the search. A lesser-known fact is that atmospheric turbulence can blur images by fractions of an arcsecond, a weather and terrain impact that limits resolution from Earth. Data pipelines grow more complex. Algorithms track potential objects across multiple frames, filtering out stars and galaxies. Even then, candidates often require manual verification. A lesser-known fact is that automated tracking systems must account for parallax caused by Earth's motion, a production issue that complicates motion detection. Training of researchers evolves further. Skills now include not only astronomy, but data science, statistical modeling, and computational simulation. The search becomes interdisciplinary. A lesser-known fact is that modern astronomical research teams often include specialists in machine learning to handle large data sets. Reflecting a crew training detail shift, small improvements continue to compound. Better sensors increase sensitivity. Faster processors reduce analysis time. Each advancement expands the searchable region incrementally. A lesser-known fact is that improvements in detector efficiency over the past decades have increased sensitivity to faint by significant factors. Alternative models are refined. In parallel, some simulations suggest that clustering of orbits could arise from past gravitational interactions or collective effects of smaller bodies. The hypothesis remains one of several competing explanations. A lesser-known fact is that long-term gravitational simulations must account for billions of orbital interactions, a computational challenge that influences model accuracy. A defining scenario unfolds in patience rather than action. A candid object is detected faintly, then reobserved. Its motion is tracked over months. Its orbit is calculated. Only then can it be classified. Most candidates fail this process. A lesser-known fact is that confirmation of a distant object can require tracking over multiple oppositions periods when Earth and the object align favorably for observation. Why the hypothesis remains viable is not certainty, but resilience. It continues to explain patterns that alternative models struggle to reproduce consistently. At the same time, it remains unproven. A lesser-known fact is that competing models are evaluated based on how well they reproduce observed distributions, not just individual cases. A command doctrine shift in evaluation criteria. The cost of this phase is persistence under uncertainty. Years of work may produce no definitive results. Progress is measured in narrowing possibilities rather than making discoveries. A lesser-known fact is that null results finding nothing in a predicted region are scientifically valuable as they constrain models and refine search parameters. Fatigue becomes structural. Projects extend beyond individual researchers, requiring continuity across teams and generations. The search becomes institutional rather than personal. A lesser-known fact is that long-term surveys often involve multiple institutions, sharing data and resources to maintain continuity. Meanwhile, technological horizons expand. Future observatories promise deeper imaging and wider coverage. These tools may either reveal the planet or eliminate large portions of possible parameter space. A lesser-known fact is that upcoming survey telescopes are expected to detect objects several magnitudes fainter than current limits, dramatically increasing detection potential. The hypothesis adapts with each constraint. Regions of the sky are ruled out. Orbital parameters are refined. The search becomes more focused over time. A lesser-known fact is that iterative exclusion of search can significantly reduce the volume of space needing observation, improving efficiency. Public attention continues to fluctuate. Interest rises with new studies, then fades. The hypothesis remains present, but not dominant in popular discussion. A lesser-known fact is that scientific topics often experience cyclical public attention patterns tied to publication and media coverage. Replacement, if it occurs, will likely come through accumulation. Either detection confirms the existence of the planet, or alternative explanations gain stronger support through data. A lesser-known fact is that scientific consensus typically emerges gradually as evidence accumulates, rather than through single discoveries. Its legacy continues to form regardless of outcome. The search drives innovation in observation, modeling, and data analysis. It expands understanding of the solar system's outer regions. A lesser-known fact is that exploration of distant solar system has led to discovery of new classes of trans-Neptunian objects. What remains at the edge is distance itself. The outer solar system is vast, dim, and slow to reveal its structure. Exploration is limited not by secrecy, but by physics. A lesser-known fact is that light travel time from objects hundreds of astronomical units away can be measured in hours, emphasizing observational delay. And so the story continues, stretched across space and time. The possibility of a ninth planet persists, not as a hidden truth withheld, but as a question still being tested. One observation at a time, one refinement at a time, under conditions that demand patience more than certainty.